Hi everyone, we are from Binary Nexus and I am Tan Zhaoxuan.
I am Leong Pilan.
I am Lim Jihang.
4-bit 4-to-1 mux is one of the parts in ALU design. Before implementing 4-bit 4-to-1 mux in Quartus, a 1-bit 4-to-1 mux should be designed first. By referring to the function table shown at the bottom right of the screen, the logic circuit of the 1-bit 4-to-1 mux is implemented using 4 3-input AND gates, 2 inverters, and a 4-input OR gate. The next step is to compound the design by clicking Analysis and Synthesis button. Next, we are going to run the functional simulation to see the result of the waveform. As you can see from the function table, when the selecting input S1 equals to 0, S0 equals to 0, the output Y will show the same waveform as I0. S1 equals to 1, S0 equals to 0, the output shows the waveform same as I2. S1 equals to 0, S0 equals to 1, waveform of I1 will be at the output. S1 equals to 1, S0 equals to 1, waveform of I3 will be shown at the output. After verifying its function, we can move on to create a symbol of the 1-bit 4-to-1 mux to initiate the design of two 4-bit 4-to-1 mux with 4-bit inputs A0, A1, A2, A3, and B0, B1, B2, B3. In this design process, bus lines are used to represent 4-bit binary numbers in the input and also the output. Then we proceed to the verification step for both 4-bit 4-to-1 mux. Let's jump to the waveform simulation of the 4-bit 4-to-1 mux with the 4 bits inputs A0, A1, A2, and A3, which is similar to the waveform result of the 1-bit 4-to-1 mux. When the selecting input S1 equals to 0, S0 equals to 0, the output Y will show the same waveform as A0. S1 equals to 0 and S0 equals to 1, the output shows the waveform same as A1 and so on. Similar operation goes to the waveform simulation results for the 4-bit inputs B0, B1, B2, and B3. Last but not least, creating the symbols for both 4-bit 4-to-1 mux are necessary for the design of the ALU.
We will start the design with 1-bit full adder, then compile an analysis to verify the functionality of the design. Then we'll move on to the waveform simulation results that shows all the possible input combinations for the 1-bit full adder. For example, let us look at the last input combination, where input A, B, and carry in equals to 1. The output produced is sum equals to 1 and carry out equals to 1. In binary terms, A plus B equals to 1, 0. So when adding carry in, the final sum is equals to 1, 1, where the most significant bit is carry out and the least significant bit is sum. Next, we'll move on to the logic circuit design of 4-bit full adder and subtractor. We need to compile an analysis to verify the functionality of the design too. Then, let us look at the waveform simulation results that show several feasible input values for the 4-bit full adder and subtractor. For example, let us look at the first input combination, where input A equals to 0010 and input B equals to 1101. Where ALU op equals to 0, the subtraction operation is performed and gives the output equals to 0101. Where ALU op equals to 1, the addition operation is performed and produces the output 1111.
Next, we will do the 4-bit register, which include 4 bits of input and also 4 bits of output. You take the input based on the clock edge and also the reset input. You build the 4-bit register using 4 1-bit register, which in this case, we use the built-in D flip-flop in Quartus Prime, which include D input, Q output, a clock input, and a reset. For 1-bit register, it is positive edge trigger. When the clock edge is positive, the output will be equal to the input. When the clock edge is not positive, the value of output will be whole. Same goes to 4-bit register. When the clock edge is positive, it will read the input and output the same value. The value will be whole until the next positive clock edge is detected. Finally, we integrate 4-bit multiplexer, 4-bit adder or subtractor, and 4-bit register to build the ALU design with 13 input pins and 1 output pin. When reset equal to 0, all the output value will be reset to 0. When reset equal to 1, it operates as usual, following the clock pulse. When it is positive clock edge, you read the A SLI value and B SLI value. In this case, A SLI is 1, 1, indicate 0, 1, 0, 0. And B SLI is 0, 1, means B is 0, 0, 0, 1. Then it goes to the 4-bit adder or subtractor. The ALU operation here is 0, means subtraction. Then the result of subtraction will go through the 4-bit register, then the output of ALU will be this. Here is a table to show all the output of this simulation result. In conclusion, this ALU design used 2 4-bit multiplexer, 1 4-bit adder or subtractor, and 1 4-bit register to undergo the function of select bits, arithmetic operation, and also store data, with the least number of logic gates used.